On page 503 of his book Black Holes and Time Warps, the physicist Kip Thorne introduces the idea of a time machine based on the time dilation effects found in special relativity. The time machine also relies on the creation of a wormhole. A number of people have challenged the validity of the time machine by showing that the wormhole would require negative energy to keep it open. In this video, I tend to show that the underlying idea behind the time machine is invalid, and so would not work even if the wormhole could be generated and maintained. One quick point I would like to remind everyone of is the distinction between what an individual sees and what that person's frame measures. The frame will measure something wherever it is and at any time, not necessarily where the observer is. I will call this measuring. The observer will only see an event at some location other than where it is, after light has had time to reach it from that event. I will call this seeing. Thorne's setup consists of two experimenters, whom I shall call Helena and Alison. Each will be in a chamber. In Helena's case, the chamber is an office on Earth that remains at rest, ignoring the Earth's station in orbit, etc. In Alison's case, the chamber is a control room of a spaceship that can travel at a relativistic speed. They also share a wormhole. One end is in Helena's office and the other is in Alison's control room. At the start of the experiment, Alison is on Earth so that Helena and Alison can hold hands through the wormhole. Alison then takes off on a relativistic journey around local space, finally returning to a starting place. It is assumed that throughout the trip the internal length of the wormhole remains constant so that Helena and Alison can keep holding hands. Once Alison returns to Earth, she has, due to time dilation, aged less than Helena. It is Thorne's supposition that this puts her at a different time, and thus if Helena crawls through the wormhole, she will enter Alison's earlier time zone. In other words, she has gone back in time. It is my assertion that although Alison has experienced less time, she has merely aged less rather than gone back in time. For my version, I will add a camera and display to both chambers. This is so that we have a specific record of what each sister personally sees at her current location. Outside there will be a series of clocks synchronized to the stationary sister's frame. This view will be referred to as the external clock. Note, in this diagram the horizontal scale for distance travelled is massively different to the scale for drawing the chambers. The two chambers will effectively on top of each other. This will be a bit messy at the start, but both clocks are just about legible and it will make subsequent diagrams clearer. We will start with a non-technical discussion. If Alison goes on a relativistic journey relative to Helena, her clock will slow down compared to Helena's. We'll assume in this example it goes at half speed. So when Alison returns home, she will see Helena's clock having advanced twice as far as her own. For example, her own clock will be at 1 p.m. and Helena's at 2 p.m. She can hold her own clock next to Helena's to compare them directly. If Helena stands next to Alison, she will see exactly what Alison sees, i.e. Alison's clock at 1 and her own at 2. If, on the other hand, Helena's goes back through the wormhole to reach Alison, she will still see what Alison sees, i.e. Alison's clock at 1, her own clock at 2. So Helena still sees her own present. If time travel had really occurred, and Helena had gone back an hour, then Alison's end of the wormhole would still be travelling and not yet back home. If Alison were back home when Helena comes through the wormhole and time travel had somehow occurred, then Helena would have to see Alison's clock reading 1 and also her own clock reading 1. So one way the clocks will look the same, the other way they will look different. This is a contradiction. Alison would have aged less but not gone back in time. We will now perform a more detailed analysis of the journey. For our analysis, we will send Alison on a journey at a velocity of about 0.8660 times the speed of light relative to Helena, who is considered to be the rest frame. This will give a gamma factor of 2. The clocks will show the hours elapsed from the start of the journey. All distance in space will be in light hours. This gives the light speed as 1 light hours per hour. The clock shown in the diagram will be set at 1 light hour intervals, but it is assumed that will be a clock at every intervening position. So wherever Alison is, she will see via her camera one of Helena's synchronized clocks. Helena will see herself at rest, her clock ticking in step with her external clock array. What does her frame measure concerning Alison? As Alison is moving relative to her, Helena will see Alison's clock running at half speed. Helena will also measure Alison as being next to one of her own synchronized reference clocks, and so she will measure Alison's external clock as reading the same as her own time. Thus, as far as Helena is concerned, whatever time Alison thinks it is, she is still observing Helena's present. Alison will not be seeing what occurs in Helena's world at a time corresponding to her own clock time. So as Alison's clock slows down, she observes Helena's world speeding up. Now I know what you are thinking. From Alison's perspective, she is at rest, and it's Helena who is moving, and so she should see Helena's clock running slowly. I will cover this next. To show that Alison's view does in fact correspond to that of Helena, we need to do a full analysis. There are 2 effects of relativity that need to be taken into account. The first is the retardation of Helena's clocks as seen by Alison. The second effect is the loss of synchronization. If 2 clocks are synchronized in one frame, they will not be synchronized as seen from a frame moving relative to it. This is covered by the term leading clock's lag. In these equations, Tm is the time on the moving clock aligned with xs, its position in the static frame. Note also that in our example, Helena's frame will be moving in the negative x direction, so the velocity will be negative, hence the minus sign disappears. You start with the Lorentz equation for the time on the moving clock. By setting the time on the static frame to be 0, we get a simple equation for the clock lead, because we are only interested in the clocks that are following Helena. If you have done this sort of thing before, you may be surprised by the extra gamma. This is because the equation is usually done for xm. Expressing xs in terms of xm will have the extra factor of gamma. This is how the clocks will appear in Alison's frame. The clock retardation formula is the simple 1 over gamma. The clock in Alison's frame that reaches Helena at time ts would have started at position xs equals vts. So this should be used as a value of xs in the clock lead formula. This will lead to the final formula below. This can be simplified as shown. Finally, we will get the formula That is the definition of gamma. This is exactly what we require for Alison's view to match Helena's. We now have the full view of Helena's frame as seen from Alison's frame. You will always see Helena's actual clock shown only half the time on Alison's, but the clock passing Alison will always read twice the time on Alison's, so if Helena crawls the wormhole, she will still be only in her present. So in conclusion, this time machine design itself is invalid.